All right, we're going to ignore the time. We're going to pretend that the time doesn't exist in the corner. Just hold your hand over it because this is the only time I've got to do it. But we're going to look at an annuity and how we can solve these kind of problems because they're a little bit difficult and they've got a little bit of finesse to them. So we're going to solve them by creating a series and a recurrence relation. So a lot of these problems, particularly ones you'll see in different kinds of textbooks, they're going to ask you to solve it a certain way, and we can get around that, by solving it one way and generalizing it from there. So here's what we're going to do. Heath decides to save M each month, deposits it at the start of each month at an account paying 9% interest compounded monthly. Let AM be the amount in the account after M months. We want to show that A2 is this and that AN is this. Both of them are really going to be combined into the same question. So let's look at A1. The first amount that gets plugged in is going to be M, the monthly repayment, or the monthly payment, I should say, if I say repayment. Pretend I didn't. 1 plus 0.09 over 12. 1 month, 1 month of repayment, 1 round of interest being charged on it. I'm just going to put that in the calculator. Remember, I've wrote my interest as a decimal, and I'm just going to let it go through to the keeper. So M, 1.0075. I'm going to leave it there. Now, when I'm looking at the second amount, here's what I'm looking at. The second amount in terms of interest works as follows. It's going to be the initial amount. Interest is charged on the initial amount. That is okay. There is interest charged on the initial amount, plus the new payment that is going in. That's what's happening right there. So we're going to stop right there. In terms of what we are looking at, the new payment is also being charged interest. So we're just going to put that in. I don't know, it's 65, it's 75, and it's 0.000075. The new payment is also being charged interest, so we're going to stop. Now, what I'm essentially doing is substituting A1 into there. So it's going to be M bracket 1.0075, 1.0075 plus M 1.0075, which means that right there, it's going to be M 1.0075 squared plus M 1.0075. So that's A2. Now, this kind of pattern follows really well. So what do I mean by that? Well, what I mean by that is if we're looking at A3, A3 is A2. It's going to receive the same amount of interest, which is 9% per annum, compounded monthly, and it's the same that we've been seeing all this time, plus a new amount that is also being compounded because it's deposited at the start of each month. So he's depositing it, and that's also receiving interest. So if I put A2 into here, what is eventually going to happen is if I take that and I multiply everything in there by 1.0075, I'm going to end up with M 1.0075 to the 3 plus M 1.0075 squared plus the most recent payment, that one I'm just boxing right there, 1.0075 to the 1. You can see the pattern that this is making, and this is a pattern that will be available for AN, where I'm talking about N deposits. Heath can deposit as many amounts M payment as he wants, but that value N, it's going to follow the same pattern, which is going to be, you can see what's happening here. It's going to be M 1.0075 to the N plus 1.0075 to the N minus 1. You can see the pattern that's happening here. Plus, and it's going to go down forever. And it's going to go down until we get to the most recent payment, which is again gaining interest. This is where we get to fudge around a little bit. We get to work on what we're actually looking at. We can create a series by factorizing out M to the 1.0075. That is the smallest term everything has. Every single term in this AN series has got M, and it's got one of these powers because this right there is my smallest term. If I factorize that out, we've got 1.0075 to the M minus 1 plus 1.0075 to the n minus 2 all the way down to 1, because that is what I'm factorizing out. And the reason I'm factorizing that out is because that is common in all terms. That's there in every term. Oh, we're about to fucking ride to up. Oh, I swore. I'm not repeating this. I'm not doing this again. I've done this too many times. I've restarted 3 times today already. I'm not restarting again. Pretend you didn't hear that. So, what the second part ends up being is it ends up being a series. This second part here that I'm underlining in a different color is actually a series. So I've got that part that's outside, and I've got this part that's here. It's the sum of a geometric series because I'm summing all of the terms from the first term to n minus 1. I'm putting all of those terms together. I'm bringing them all in, and it's a geometric series. Remember, geometric series is Sn a r to the n minus 1 over r minus 1. So my initial term is 1. So I'm going to put that in as 1. My multiplier, you can see what it's going up by. It's going up by what's in the brackets, which is my interest rate to the n minus 1. Remember, that's all in brackets. We probably won't need it because we're multiplying it by 1 over 1.0075 minus 1. So we have that right there. Now, if we do a little bit of fancy manipulation, and by fancy manipulation I mean we pretend that I'm not actually running out of space, we subtract 1 from this. We have m 1.0075. This is what we've got, 1.0075 to the n minus 1 over 0.0075, because I'm doing 1 point minus 1. Now, if we do a bit of fancy footwork, I'm going to do this divided by that, and I'm actually going to end up with 403m over 3, 1.0075 to the n minus 1. Which is what we're actually being asked to produce. So I should get that, type it in your calculator, check. I'm running out of space, so we've got to really ride the wave with me right here. That is what we end up with. And that whole process that I've just done is the biggest thing that we're actually going to be doing over the next couple of lessons and things like that. So while I delete all of this, just, skip a couple of minutes. That is how we get there. That whole process we should be doing every time, no matter how the question asks us to do it. The Cambridge textbook, it's going to want you to do it. This is called the recursive method. A lot of them want you to do it like manually or something. It's not pleasant, basically, is what it is. It just revolves around a lot of different things. So that right there is what we're going to be looking at, and that is the method we will use every time. It is confusing, and it does take a lot of practice, and you're going to set it up the same way every time. So if you're not sure, follow this example by looking at another one. So if Heath invested $200 a month, how much would he have in 4 years? So M is 200 and N is 4 times 12, because remember, this whole thing is monthly. That's a really big part about it. So we sub in 48 into n, so we have 403 times 200 over 3. We're going to use this series here because that's what we ended up reaching. We have 1.0075 to the 48. Remember, it's in months. It's all in months. So we have 11590.42. That's how we've ended up with it. How much would be invested? That's how much would be invested. Now, you can do a lot of these by manipulating them. I'll quickly do the other one. So like D, Heath wants to save 10,000. This time AN is 10,000. So we've got 10,000 is equal to 403m over 3, 1.0075. And we're looking at the power of 60 this time. Why are we looking at to the power of 60? Because it's 5 years and it's all done monthly. Now, divide this by that power right there. We're going to divide both sides by that power. And once we do that, I'm just simply going to say we're going to divide both sides by what's in the brackets. Then we're going to times it by 3 because we're doing the opposite. Then we're going to divide by 403. I know it seems like a lot. I'm just really running out of space. So we have the monthly repayment as 131.60. a lot going on, but it's the idea about doing the opposite. Divide both sides by what's in the brackets. Multiply by 3. We want to remove the denominator. Then we're going to have 403m equals something. Divide by 403. We end up with what's required. And then we have the final thing. He can save $2,000 a month. How long will it take him to save a total of 150,000? So these problems, anytime you're looking at the time, how long or anything along those lines, you're actually going to be using logs, and we will always be doing this. So anytime you look at a financial question and it's about how long, it's always logs. Always, always, always. So we know that the monthly repayment M is $2,000. We know that AN is 150,000 because that's how long we want to work out what it wants him to save. We've got AN, it's already there, 150,000 equals 403 times 2,000 over 3, 1.0075 to the N. We don't know what that is, minus 1. We've got that right there. What we're going to do is we're going to multiply both sides by 3, divide by 403 times 2,000. That's what we're going to divide by. Again, we're doing the opposite. Whatever that number is, I'm getting rid of it. I had my calculator. I've accidentally moved it. We'll let it go through to the keeper. And then what I end up with is 1.0075 to the n minus 1 equals 628 over 403. 628 over 403 is what you should get if you're taking 150,000 right here. You multiply that number by 3 and you divide it by 403 times 2,000. That's what you should end up getting. I'm going to add 1 to both sides. That is what I get after I add n plus 1 to both sides. So I have 1.0075 to the n equals 628 over 403. So yeah, that's what I should get after I've added the 1 from this. So, but everything else that it says still stands. Then anytime I have like this, I'm going to take the log of both sides. And that's a really important feature of what we're going to do. And now, remove my log laws. I can move this around the outside. N times ln 1.0075 equals ln 628 over 403. And I'm going to divide both sides by ln 1.0075. And I end up with 59.36 months. Remember, everything in terms of time period is months. It's all months because I'm dividing my interest rate by 12, which means it's going to be 60 before he ends up with a total of 150,000. There's a lot going on here. Break it down, do it slowly, take your time. Try the second example. Do not try the second example. Try one of the examples in your textbook from the questions that I've given you on the classroom, but only do the method that I've done. Forget everything else, because you will always end up with the same answer. It's a series in financial. It's hard.